In a previous video, we've built up this table that's going to allow us to figure out what mechanism a reaction happens by. And in 842, they're not expecting us to draw the products, but they are asking us to identify the mechanism for several different reactions. Now, in all of the reactions, the substrate is 2-bromopentane. And the prefix is pent, so we have 5 carbons, 1, 2, 3, 4, 5. The infix is AN, so all single bonds. The suffix is E, so it's a hydrocarbon. I'm drawing the molecule, so I can number it however I like. I'm going to number it from left to right. We have a branch on carbon number 2, and it's a bromine. So we have a bromine coming off of carbon number 2. And what you would want to notice in this molecule, this 2-bromopentane molecule, is that the leaving group is on a carbon that is secondary. That carbon is bonded to 2 other carbons, so it is a secondary carbon. Now, in terms of thinking about what type of mechanisms that can happen, that substrate can undergo, we'll be looking at this second row here. This row tells you the mechanisms you can get when the leaving group is on a secondary carbon, like it is here. Okay, what'll be different is what type of a nucleophile or base we have in each of these scenarios. So first, what if we had sodium ethoxide? If that were our reagent. Well, sodium ethoxide is a strong base and a strong nucleophile. You can see it right there. And that, when that column overlaps with the row we're interested in, you'll see that you get 2 products. You will get the E2 product, and that will be our major product. And we'll also get an SN2 product, and that would be our minor product. Now, this exercise isn't asking us to draw them, but just to identify the mechanisms we'd use. So that's that one. Now we're going to use 2-bromopentane for all of these reagents, and so we're going to stick with this row, where the leaving group is on a secondary carbon, just like it is in 2-bromopentane. So what if we had sodium iodide? Well, sodium iodide and DMSO, it's a polar aprotic solvent. If we were just doing substitution reactions, that would favor an SN2 mechanism. Well, weak base, strong nucleophile, that's sodium iodide. You can see sodium iodide right here. It's a weak base and a strong nucleophile. And what that means, is that we're in this column, and that overlaps with the row that we're interested in. Where that overlaps, you get an SN2 mechanism. And so that's probably why they gave us dimethyl sulfoxide, that polar aprotic solvent, to aid in this SN2 mechanism. Okay, so we're still dealing with 2-bromopentane, so our leaving group is still on a secondary carbon. Well, what if the reagent we used was sodium hydroxide? Sodium hydroxide is a strong base and a strong nucleophile. So we're in the second column, where that overlaps with the row that we have. We see that we get 2 products. We get an E2 product, which is our major product, and we get an SN2 product, which is our minor product. In this next one, we have potassium tert butoxide, TBUOK. And for TBUOK, this is really an R group. So this is R, O, and then we have a metal. Here it's potassium, but it could just as well be sodium. So you could see that that's really NaOR. That's a strong base and a strong nucleophile. And so we'll get 2 products. We'll get an an E2 product. That's our major product. And we'll have an SN2 product. And that would be our minor product. And so this is just another example of how we can use this table, and we discussed at length how we got all the information in this table. But now that we have it, you could see how quickly we can glance at the substrate and how substituted it is. And each each nucleophile and base, and by comparing those, we can see exactly the type of mechanism we have, which puts us very, very close to knowing what type of product we'll get.